welcome to the Deep Dive. Today, we're diving into the world of machine learning. You've sent over a ton of excerpts, articles, research snippets, really all about the fundamentals. So we're aiming to give our listeners a solid grasp of all the core concepts, how those models are actually trained, how you can even judge if they're any good, and then what it all means in the real world.
Yeah, it's a great mix of sources, and they cover everything from the history of the field to some of the latest techniques. We'll definitely get you up to speed.
All right, so everyone's always throwing around the term machine learning these days, but instead of just like hitting the definition, can we just jump into an example of how it's different from just regular programming?
Absolutely. Let's just say you're building that classic spam filter. So a programmer, they might write a bunch of rules, right? So like if it contains free money, it's spam. But machine learning, it kind of flips that on its head. So you just feed the algorithm a ton of emails. They're already labeled spam or not, and then it figures out the patterns like all by itself.
So it's like the computer's learning from experience, kind of like,
Right.
how we learn.
Precisely. Yeah. And this learning is what lets machine learning adapt to these subtle cues that hard-coded rules would totally miss. It's actually why spam filters today can catch even like cleverly disguised junk.
That makes sense. Now, one thing that just keeps popping up in these articles is the huge importance of data. It's almost like data is the lifeblood of this whole machine learning thing.
Yeah, couldn't have said it better myself. Machine learning algorithms, they're completely dependent on data, but it's not just about like the amount of data. It's about understanding its characteristics. One article actually talks about the 5 V's of big data, which I think perfectly illustrates this.
Oh, yeah, I saw that term, volume, velocity, variety. What were the other two?
Value and veracity. Imagine like a company trying to personalize product recommendations. So they have tons of data, that's volume. It's constantly, streaming in from website clicks and purchases, that's velocity. And it comes in different forms, browsing history, ratings, social media activity, and that's variety.
Okay, I'm starting to see how all these V's paint a picture of just how complex the data can be.
Exactly. But here's the kicker. If that data is full of errors or inconsistencies, right, that's low veracity, the recommendations will be way off. And if they don't actually use the insights to improve the customer experience, so they're ignoring the value, it's a wasted effort.
So it's like having all the ingredients for, a gourmet meal, but not knowing how to cook.
Yeah.
Or serving it to people who, just hate that kind of food. What a mess.
A perfect analogy. And that leads us to the heart of it,
Yeah.
building a machine learning model. Think of it like training a chef. First, you need to prep all those ingredients. That's your data pre-processing.
So what are some of the techniques used to prep the data for a machine learning model?
There's a few key steps. So you might have, missing values in your data set. Let's say you're predicting house prices and some listings are missing the square footage. You could remove those listings or, fill them in with the average square footage. Or you could even train a separate model to predict the missing values based on other features.
Wow. So there's a lot of thought that goes into even the initial data preparation stage.
Absolutely. Another step is, encoding categorical data. Imagine a feature like house style with values like ranch, colonial, modern. You need to convert, those text categories into numerical representations that the algorithm can actually work with.
So you're essentially translating the data into a language that the machine can understand.
Precisely. And then there's, feature scaling. So some features might have much larger values than others, like square footage versus number of bedrooms. Scaling ensures all features contribute equally to the model.
Okay, that makes sense. So once the data's, prepped and ready to go, what happens next?
This is where things get really interesting. We need to pick the right recipe, or in machine learning terms, the right algorithm. A common category is supervised learning, where we teach the model using labeled data.
Okay, so it's like you're showing the model a bunch of pictures of cats and dogs and telling it which is which.
Exactly. A classic supervised learning algorithm is linear regression. Let's say you're, predicting house prices. You could train a linear regression model using data on, square footage, location, number of bedrooms, and so on. And you use the actual sale prices of those houses. The model would then learn to predict the price of a new house based on those features.
So it's finding the relationship between those features and the target variable, which is the price in this case.
Right. And then you have logistic regression, which is, used for classification tasks. So instead of predicting a continuous value like price, it predicts a category, like whether an email is spam or not.
So with logistic regression, the output is a probability of belonging to a certain category. Like there's a 95% chance this email is spam.
Exactly. And there's a whole world of other algorithms out there. Each one is suited to different tasks and data types, and we'll explore some of those a little bit later. But before we get too carried away with algorithms, we need to talk about something crucial. How do we even know if our chef or our model is any good?
That's a great point. We don't want a chef that can like only make one dish or, even worse, makes everything taste terrible.
Mhm.
How do we evaluate the performance of a machine learning model?
That's where model evaluation comes in. It's all about understanding how well our model generalizes to new, unseen data. We don't just want it to like memorize the training data. We want it to actually perform well in the real world.
Right. Like our chef needs to be able to adapt recipes and cook for like different tastes,
Mhm.
not just repeating the same dish, over and over.
Exactly. For regression tasks where you're, predicting a continuous value like price, you might use metrics like mean squared error or R squared score. And those can assess how well the model's predictions match the actual values.
And for classification, where we're predicting categories like spam or not spam.
You have, metrics like accuracy, which just tells you the percentage of correct predictions. But be careful with accuracy. Sometimes it can be misleading, especially if you have an imbalanced data set.
What do you mean by imbalanced?
Imagine you're building a fraud detection model, and only 1% of transactions are, actually fraudulent. A model that simply predicts not fraudulent every time would still have 99% accuracy.
Oh, wow. That makes sense. So it's not just about, getting the highest accuracy possible. It's about choosing the right metric for the specific problem.
Exactly. And often it's not even about maximizing a single metric. You might need to find a balance depending on the context. Like in fraud detection, you might prioritize catching as many fraudulent transactions as possible, even if it means like slightly more false positives.
So there's a lot more nuance to model evaluation. It's not just a simple pass or fail.
Right. It's more like a report card with different grades for different aspects of the model's performance. And just like with students, you want to see improvement over time.
This is already giving me a much deeper understanding of how machine learning actually works. But we've mainly talked about, linear and logistic regression.
Yeah.
What about other algorithms? What else is out there?
Oh, there's a whole buffet of algorithms beyond the basics. One that's particularly easy to visualize is the decision tree. Imagine a flowchart, right, where each node, it represents a decision based on the feature. You follow the branches down like a choose your own adventure story, and then you reach a prediction.
So it's like a step-by-step process of elimination.
Precisely. Say you're trying to predict, if someone will buy a product based on their age, their income, their browsing history. The first node might ask, like, is the person over 30? If yes, follow one branch. If no, follow another, and so on, right, until you reach a leaf node that just says likely to buy or, unlikely to buy.
I can see how that would be really easy to interpret and explain to someone, even if they don't know much about, machine learning.
Exactly. And then you have random forests, which are, essentially ensembles of decision trees. They're working together to make a prediction. Think of it like having a panel of experts. Each one has their own perspective, and they're all combining their knowledge to make a more accurate judgment.
So instead of one chef, you have a whole team of chefs working together to create the perfect dish.
You got it. Random forests are known for their accuracy, their robustness. They can handle different data types, and they're less prone to overfitting, which means they tend to generalize well to new data.
We've covered quite a bit of ground already. Data
Mhm.
preprocessing, different types of algorithms, and even how to evaluate, the performance of a model. Is there anything else we absolutely need to know before we, move on to more advanced topics?
There is one more, crucial concept that we haven't discussed in detail yet, and that is dimensionality reduction. Remember how we talked about the 5 V's of big data, especially like variety and volume? Well, sometimes having too many features can make our models, really slow and complex. Dimensionality reduction techniques help us simplify the data while preserving the most important information.
So it's like decluttering our data, getting rid of the features that aren't really adding, any value.
That's a great way to put it. Imagine you're trying to to predict customer churn. Whether a customer will stop using your service. You might have a ton of data points about each customer: age, location, purchase history, website activity, social media engagement, and so on.
Well, that's a lot of information to process.
Exactly. But some of those features, they might be irrelevant. They might even be redundant. Dimensionality reduction helps us identify and keep only the most important features, and that makes our models more efficient and sometimes even more accurate.
Okay, I'm starting to see how dimensionality reduction it kind of fits into the bigger picture of building effective machine learning models. But what are some of the techniques used for this decluttering process?
One of the most popular techniques is called principal component analysis, or PCA. It's a bit math heavy, but the basic idea is that it finds a new set of features called principal components that are linear combinations of the original features.
So instead of using all those individual features, we create new features that combine the most important information from the original ones.
Exactly. And the cool thing is that you can often reduce the number of features, significantly without losing too much information. This makes the models faster to train and often improves their performance.
So dimensionality reduction is like finding a more compact and efficient way to represent our data without, without sacrificing too much detail.
Precisely. It's another tool in our machine learning toolkit, and it helps us build better, faster, and more insightful models. And speaking of building better models, there's this another concept we kind of need to unpack: the bias variance trade-off. It's like a bit of a balancing act in machine learning.
Okay, I'm intrigued. What exactly is like bias and variance in this context?
So think of bias as how much our model's predictions are systematically off from the real values. Like imagine you're trying to like draw a straight line through a bunch of points that clearly form, a curve. No matter how you angle it, that line's it's going to miss the true relationship.
So high bias model is too like simplistic. Like it's overgeneralizing and missing the nuances in the data.
Spot on. No, variance, that's about how much, our predictions kind of jump around depending on the specific training data we used. Imagine a student who like memorizes all the answers for one test. They might ace that test, but then completely bomb any other version.
So a high variance model is too sensitive. Like it's overfitting to the quirks of the training data, and it won't generalize well to new stuff.
Exactly. And the tricky part is there's this inherent tension between those two. If we make our model super complex to reduce bias, we often increase the variance. Simplify too much, and the bias goes up.
So it's like finding that sweet spot, between a model that's too rigid and one that's too flexible.
Exactly. A lot of techniques in machine learning, like regularization, they're all about finding that balance. It's about preventing the model from getting so caught up in the training data that it doesn't work on anything new.
This kind of reminds me of those cooking shows where they talk about balancing flavors. You don't want one ingredient to just like overpower everything else.
Perfect analogy. And speaking of different flavors, we've focused a lot on supervised learning, where we have those like neatly labeled data sets. But there's a whole other world of machine learning where the data isn't so organized, unsupervised learning.
Right. I remember reading about that. It's where the algorithm has to kind of find patterns on its own without those, this is a cat, this is a dog labels.
Precisely. It's like exploring a new city without a map. And one of the key tasks in unsupervised learning is grouping similar data points together.
Okay. So if we had data on customer purchasing habits, a clustering algorithm might group together the people who always buy like coffee and croissants in the morning.
Exactly. That's actually how companies do things like customer segmentation, finding groups of people with similar behavior so they can target them with specific marketing campaigns.
Yeah, that makes sense. But how does the algorithm even know what features to use for grouping? It's not like someone is like telling it, look for people who like coffee.
That's the beauty of it. The algorithm, it analyzes the data and figures out those relationships all by itself. It might find that people who buy coffee also tend to buy pastries, or that people who buy running shoes also buy, workout clothes. These patterns, they emerge from the data without, any explicit guidance.
It's like the algorithm is a detective piecing together clues to solve a mystery.
Great analogy. And just like a good clustering algorithm, it needs the right tools, Remember, dimensionality reduction, it can be super helpful here too.
Oh, right, because we might have tons of data points on each customer, but not all of them are relevant for clustering.
Exactly. Dimensionality reduction helps us, simplify the data, focusing on the features that are most important for separating the groups. It's like filtering out the noise and getting a much clearer signal.
So it's not just about throwing like a bunch of data at an algorithm and hoping for the best, right? It's
Yeah.
about understanding the data, preparing it properly,
Okay.
and choosing the right techniques to extract, meaningful insights.
Couldn't have put it better myself. And that brings us to another fascinating area of unsupervised learning, anomaly detection.
Anomaly detection. What's that all about?
It's about finding the outliers, the data points that don't really fit the usual patterns. Think of it like finding the needle in the haystack.
Okay, I can see how that would be useful. Like in fraud detection, you're looking for those, unusual transactions that might signal something fishy is going on.
Exactly. Or in manufacturing, anomaly detection can help identify faulty products before they even leave the factory. It's all about finding those deviations from the norm that might indicate a problem.
So how does an algorithm even know what's like normal and what's an anomaly?
There are different approaches. So some algorithms they learn the normal patterns from the data and flag anything that deviates, significantly. Others they use statistical methods to identify data points that are statistically improbable.
So it's like having a machine learning watchdog. It's
Yeah.
it's constantly monitoring the data for anything suspicious.
Precisely. And the applications are vast, from cybersecurity to healthcare to financial markets. Anomaly detection is playing an increasingly important role in helping us identify and respond to, potential risks, potential opportunities.
This is really making me appreciate the breadth and the depth of machine learning. We've covered supervised learning, unsupervised learning, dimensionality reduction, and now anomaly detection. It's amazing how many different problems can be tackled with these techniques.
It really is a powerful toolbox. And there's still one more major branch we need to explore, reinforcement learning.
Oh, right, reinforcement learning. That's the one where the algorithm learns through like trial and error.
Yeah.
Like a robot navigating a maze.
Exactly. It's a completely different paradigm from supervised and unsupervised learning. In reinforcement learning, we have an agent that interacts with an environment and learns to take actions that maximize a reward.
So instead of having like labeled data or trying to find patterns, the algorithm it's actively learning by doing.
Precisely. Think of a self-driving car. So the agent is the car's AI system. The environment is the road, with all its obstacles and traffic. And the reward is reaching the destination safely and efficiently.
So the car learns to drive by, trying different things, getting feedback, and adjusting its behavior over time.
Exactly. It's a bit like how we learn to ride a bike. We start by wobbling and falling, but through practice and feedback, we eventually master the skill.
I can see how reinforcement learning would be incredibly powerful for tasks like robotics, game playing, and even things like personalized medicine, where you
Hmm.
might have an AI system learning to optimize treatment plans for individual patients.
You got it. And it's a field that's rapidly advancing with new breakthroughs happening, all the time, from AlphaGo beating the world champion Go player to robots learning to perform, complex tasks. Reinforcement learning is really pushing the boundaries of what's possible with the AI.
This is all so fascinating. We've covered so much ground today, from the fundamentals of data and algorithms to the nuances of model evaluation and the exciting possibilities of unsupervised and reinforcement learning. It's incredible how much machine learning has to offer.
It truly is a transformative field, and we're only just beginning to scratch the surface of its potential.
Wow, I feel like we've just been on this incredible journey through the world of machine learning,
Yeah.
from the basics of data and algorithms to these, mind-blowing applications like self-driving cars learning from experience. It's amazing how far this field has come.
It really is remarkable. And to think just a few decades ago, a lot of these concepts were purely theoretical. And now they're actually powering these technologies that are shaping our world.
It's true, but with all this progress, it also feels like we're just getting started. What are some of the areas that you're like most excited about for the future of machine learning?
Oh, there are so many exciting avenues. One area that's really heating up is the intersection of machine learning and quantum computing. So imagine the power of using quantum computers with their ability to like perform calculations exponentially faster to train and run these machine learning models.
That sounds like something straight out of science fiction. What kind of problems could we even solve with that kind of power?
It's hard to even fathom the possibilities, but we're talking about breakthroughs in drug discovery, material science, financial modeling, and even understanding the fundamental laws of the universe.
Wow, it's mind-blowing to think about the potential impact. It feels like we're on the cusp of a new era of scientific discovery.
Absolutely. Another area I'm particularly excited about is the development of more explainable and transparent machine learning models.
That's something that came up a few times in the articles that you said. Why is explainability so important?
Well, as machine learning models become, more and more complex, especially with things like deep learning, it can become harder to understand how they're making decisions, and this lack of transparency can be a problem, especially, in areas like healthcare or finance where the stakes are high.
So it's not enough for a model to just be accurate, right? We also need to understand why it's making the predictions it's making.
Exactly. Imagine a medical diagnosis system that's powered by AI. It might be very accurate in predicting whether someone has a certain disease, but if we don't understand how it's arriving at that conclusion, it's hard to trust its recommendations.
That makes a lot of sense. So
Yeah.
how do we even make these complex models more explainable?
There's a lot of research going on in this area. Some techniques they involve visualizing the decision making process of the model, while others focus on creating simplified versions of complex models that are just easier to interpret.
So it's like giving us a peek under the hood to see how the engine works.
Exactly. And this explainability, it's going to be crucial for building trust and adoption of AI systems in the real world.
It's great to hear that there's so much effort being put into
Yeah.
into making these powerful technologies more understandable and accessible.
Absolutely. And that ties into another important trend, which is the democratization of machine learning. So tools and platforms are becoming increasingly user-friendly, making it easier for people without deep technical expertise to build and deploy their own machine learning models.
So you're saying that machine learning is no longer just for data scientists and engineers. Anyone can get involved.
That's the goal. There are now drag and drop interfaces and cloud-based platforms and even educational resources, and they're specifically designed to empower anyone with an interest in machine learning to get started.
That's really exciting. It opens up so many possibilities for innovation and problem solving across different industries and domains.
Exactly. And as more people get involved, we're likely to see even more creative and unexpected applications of machine learning, emerge.
I can't wait to see what the future holds. But before we wrap up, I'm curious what advice would you give to someone who's just starting out on their machine learning journey?
That's a great question. First and foremost, I'd say be curious. Explore different resources, experiment with different algorithms, and don't be afraid to ask questions.
It's like anything else. The more you explore, the more you discover.
Exactly. And don't get bogged down in the math and the theory right away. There are tons of practical, hands-on tutorials and projects that can help you get started and build your intuition.
It's all about getting your hands dirty and learning by doing.
Precisely. And finally, remember that machine learning is a constantly evolving field. So stay up to date on the latest trends and tools and techniques, attend conferences, join online communities, and never stop learning.
This deep dive has been an incredible learning experience for me, and I'm sure our listeners feel the same way. We've covered so much ground, from the fundamental concepts to the exciting possibilities of the future. It's clear that machine learning is this powerful force that's shaping our world, and it's only going to become more important in the years to come.
It's been a pleasure sharing this journey with you. And remember, the best way to learn is to just dive in and start exploring.
Thanks for joining us on the deep dive. We'll see you next time for another deep dive into a topic that's changing the world.